Hello everyone and welcome to today's webinar, Motors 201, Principles of Electric Motors. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined the presentation using your computer speaker system by default. If you'd prefer to join over the telephone, just select phone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the question pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of the presentation. Today's webinar is being recorded and you'll receive a follow-up email within 24 to 48 hours with a link to view the recording. I'd now like to introduce our three panelists from Ward Leonard. Kevin Shepard, Director of Texas Business Unit, Dan Cook, Senior Technical Sales Engineer, and Dustin Graham, Service Manager. Over to you, Kevin.
Thank you, Cheyenne. Good morning, everyone, and welcome to our 201 entry into the Principles of Electric Motors. This is the second installment. We did one previously called Motors 101, which if you weren't able to participate in that is available on our YouTube site. And you can just go to YouTube and search for Ward Leonard, and all of our videos should be there as well. So the panelist today is myself, Kevin Shepard. I've been in the business for about 28 years, maybe a little more than that. Seems to have flown by. And then Dan Cook, who is our applications and engineering specialist, and Dustin Graham, who is our field service manager, located over in Houma, Louisiana. What we're going to do today is go over a little bit of a overview of the company, Ward Leonard as a whole, and the markets that we service. Then we'll get into the nuts and bolts of this discussion, Motors 201, which should take about an hour, maybe longer, just depending on what questions we do. Then we'll leave a little time for Q&A at the end of it. So we'll just jump right into it. So our company is a company that has 3 different locations. We're headquartered in Connecticut, where our manufacturing facility is. And that company, or that location, services a lot of military, heavy industry, oil and gas. We are an OEM for our own electric motor in the oil and gas industry. We manufacture a lot of different components for the military. We also have a facility in Houma, Louisiana, that is a full service electric motor and generator repair facility. And then we have the companion to that facility in Houston, Texas, which is where I'm located. Both shops fully capable to handle any electromechanical apparatus. We have field service dispatched out of both locations, have storage options, have modification options. Again, full service locations in Houma and in Houston. We are involved and have business interests in 5 different continents. We are a worldwide company, meaning that we do distribute our products all over the world. So the Ward Leonard brand has been around for quite a while, and really proud of what we can do and what we can offer as far as repair services, even on up to the most complex type of engineering type of services that you may need. So we can definitely help you guys out with whatever it is that you're looking for. These are the markets that we service. Definitely heavy industrial, oil and gas, the military, and then service and repair. It's pretty diverse when you think about it. From the aspect of how all of these markets work, but we do use best practice sharing from the military. We draw from that kind of a mil spec type of a situation, and we apply that to the rest of our business. Each location is ISO 9001 2015 certified, so we do have a consistent standard that we operate against. So a lot of experience in these different markets that we can deploy, in the service and repair industry. Right. So we'll jump right into this. there's different motor types. Now, this isn't inclusive of everything. In fact, there's one that unfortunately got left off of this slide, which would be DC motors. But this is what we most commonly see in the business and in our industry, from a repair and application perspective. AC induction motors, typically the most common, right? That's just about, I don't know what the percentage is, but it would be a large percentage of everything that's in the motor population would be AC induction squirrel cage type of motors. They are constant or variable speed. Very simple in operation. They can be either random wound on low voltage, can be form wound, higher and medium voltage types of things, but very basic. Minimal components. We went over that in Motors 101 what the components were to a standard AC induction motor. There's also AC permanent magnet motors, which they are a very efficient design. Because of the construction and the application of permanent magnets into the rotor or the stator, it depends on what the configuration would be, but you can get a lot smaller package in there. It's a little bit more reliable because you don't have as much electrical conductor inside of the motor. And what it says here with probably the motor of the future, that's as we're seeing the proliferation of electric vehicles, more of that hybrid type of a thing where motors are deployed in that is usually going to be the method that they go with, which would be a permanent magnet motor. Again, smaller, more efficient, very reliable in operation. But the drawback to that, and we'll talk about a little bit further on in this discussion, but there's some downside to the cost of actually maintaining the motor if there was a failure to occur. That's why it's the cost kind of equation you have to factor into that when you apply it, right? Wound rotor motors, they're still around. They used to be really, really big. We would see a lot of them in overhead hoists, cranes. Now they really are in mining, crushing, things where you have to have a lot of torque and some speed control on it. It does have the rotor. It does have a winding in it with a collector type of a ring that allows transmission into the rotor, so you get a signal in there, so you can control some speed with it. Still out there, just not very prevalent. They are with the collector rings. They're expensive to maintain. It's another piece of a graphite brush or carbon brush and a ring, so it's just more to maintain. Synchronous motors, they're typically large motors, and if you have a large manufacturing plant, large petrochemical plant, typically you'll have synchronous motors inside of your facility. They are a very good application for air compressors, large reciprocating compressors. They do have the ability to improve power factor on a highly inductive circuit because you can adjust phase angle to lead and lag, whatever that might be. So if you have a lot of motors turning on and off on a main bus, a synchronous motor can kind of soak that up and clean up the power some. So that's kind of one of the side benefits of it, but it does do that, which is nice. And they give a lot of torque, a lot of power at a very slow speed. So when you're talking about a large reciprocating compressor that needs to turn about 300 or 400 RPM, but puts out 10,000 CFM, typically it's going to be a synchronous motor doing that. The one that's left off of here, unfortunately, was DC motors. And DC motors, they have their applications. Where I see them the most is in a spooling or reeling. I mean, imagine like a paper reel, where you would have a DC motor attached to the reel. When the reel is empty, it's a lighter load, but as the reel becomes fuller, the load becomes greater, but you still need the same speed. So there's a variance in load, and the DC motor is able to adjust to that very well. It's a real workhorse of kind of the industry, but the downside to that is the maintenance cost with them. They're typically have multiple carbon brushes in it, has a commutator, a segmented commutator that has to be maintained. The carbon wears, it puts off dust. They have to have blowers that go in and cool them. So there's a lot that goes on with the DC motor. That's why it's the trend has been maybe to move away some of that and go over to an AC motor and a variable speed drive. Just kind of depends on what your plant need is, your operational needs are, but that's something that we can help you identify if you have those either eddy current drives, DC motors, anything like that, that maybe you wanted to retrofit and do a modernization on. We could help you with that, right? That's where Dan comes in, and he can look at your application, talk through it, and give you a best case scenario as to how to move forward. Right. So moving on. When we talk about the different motor types, there is also different constructions on the rotor, right? And that's what this slide is really showing, is you're looking at these bar shapes, and that's a piece of a rotor lamination is what that is. I don't know if you guys can see my cursor moving around there or not, but the rotor lamination is very similar to the stator lamination. It's all segments of steel, and they are all connected by an N-ring up here, which the bar goes through. And so that's basically how an induction motor works. The rotor gets induced with voltage or magnetism, actually, and it goes to these different these bars, and the shape of the bar really determines what the torque of the rotor is, or the motor in general. That's why I have these different bar designs, and you can see the slot design down here would be similar to that slot B type of a design. But we'll get a little bit deeper into that, as there's another slide in here that really goes a little more in depth to the shape of torque of bars, and what the design load is. But yeah, that's one of the neat things about electric motors, is that all this stuff is kind of customizable to what you need, right? So we're not just taking a standard, this is all you got, and applying it to a varying load. Like, we can go in and really just change the shape of the bars, change the shape of the rotor, change the construction of the rotor. The rotor usually is either copper or aluminum. Copper is a better conductor. It's more expensive, just because the material is more expensive. Aluminum rotors are typically die cast, meaning that they'll be like a pouring in method. So there's the potential for porosity in the end rings and even in the bars, but the manufacturing process is so much cheaper, right? You don't have to have custom bars cut and then pressed in and then welded to the end ring, because if you don't get that end ring right, that's where all the inrush current really absorbs in the end ring. So if that's not correct, that's where you see a lot of heating and separation and rotor failures. Aluminum bar rotors could potentially be more prone to rotor bar breakage just because of the construction. So typically in an API spec motor, you're going to see copper bar rotors, right? That's usually what we see when we start getting into a motor that needs to be designed to last for X amount of years. And in an API spec motor, that's what you're going to need. Very much a very heavily overbuilt type of a motor when you get into API spec, and that's copper barred, right? The permanent magnet, we just talked about this earlier, but you can see the efficiency rating here as opposed to as compared, to other premium efficiency, standard efficiency motors. The permanent magnet really does just kind of perform better, and it really has a lot to do with the conductors or the lack of conductors in there, and how close you can get the air gap and some other things. So typical applications of that would be, on this lower left-hand side, that's a thruster motor on a boat, and high torque, high efficiency, those kind of things. Cooling tower motors, another really great application, because you can direct drive that. You don't really have to come off of a belt at that point. And then, even your standard garbage disposal, permanent magnet type of a motor. The drawback to those, and I said this earlier, was that, if there is a failure, like if you get a crack in the magnet, that's a big deal. I mean, it's a lot to replace. It's a lot to maintain. If you have a really high vibration type of environment, may not be the best suited. Definitely, cannot take an impact, can't do any of those things because the magnets it's all rare earth magnets and really hard type of a material, which when you look at something that's got a hardness like that, if it takes a hit, it's going to break and crack. And then when you got that break in the permanent magnet, it's definitely going to affect the smoothness of the operation of the motor. It will create some vibration. So that's the downside of the permanent magnet. And really they're just expensive. It's expensive in materials, right? Because rare earth magnets are expensive to construct, they're hard to get a hold of, and then if you have to maintain them after that, like we had to do any replacement of the magnets, that gets really, really expensive. So that's why you don't see them applied all throughout the industry, right? It just doesn't make a whole lot of sense where you can plug in a standard induction type of a motor, squirrel cage, if you will, and the cost benefit there, even if it did fail, it probably outweighs what the initial cost of a permanent magnet motor would be. So, but definitely growing in cars and electric vehicles. I mean, that would be because of the small package and how efficient they are. When you think of how a motor has to draw current from a battery, if you can get something that's really efficient, that puts out a great deal of torque and horsepower and uses less current draw, then that's perfect for a car, right? So I think we have a poll question now. And our question today, is, are you currently using motor control devices? So if you would just take a minute and just kind of let us know, we're going to get into a little bit more of that, but we'd like to just know how many people have, or how many of you are applying an electric motor type of a control, whether that be a VFD, soft start, whatever. If you're doing, if you have those or are familiar with that technology, just click yes. And if you don't know what I'm talking about, then no. Okay, so a lot of people, the results are back. It looks like a lot of you guys are using motor control devices. We'll get into a little bit more of that, which is kind of why we asked the question, just to kind of get an understanding of if that technology it's been around for a while, but just what type of a saturation in your plants you guys are using, which seems to be a lot. All right, so talking about slip and really how a motor works, and so if you think about, and the graphic here is what it's representing would be, the stator would be the tow truck, the rotor would be the super cool Thunderbird, and if those things were direct coupled and hooked together like a tow truck, then it's that you have that relationship. It's not how a motor works, right? So basically, if you hung a magnet on the back of the tow truck and then pulled it along, it would have a little bit of a gap, right? So, and that's defined as slip, right? So, in order for the electric motor to produce torque, it does have to have a certain amount of slip, right? And you look at the bullets down here, this really gets into the explanation of why that is. So to produce current flow in the rotor speed must be slightly slower than the synchronous speed. And the difference between the synchronous speed and the rotor speed, which would be the rated speed, is called slip, right? So you're going to have an electrical rotation that has a certain frequency to it and a certain speed. And the rotor follows that, but it's not quite at the same rate. So if it's, that's why you'll have, if something's rotating 1800, we'll see RPM on a nameplate shown at like 1750, on a 4-pole motor, but it's going to be slightly less. And that's why, because you have this rotating magnetic field, then the rotor is induced, and then that follows, or as the magnet is pulling it around, it kind of follows it, so it's slip, and then through that slip you get torque. Moving on to the nameplate, we'll spend a little time here, really, because from what we do in the repair side and even how you apply your motors, this data plate is critical information. And on the repair side of things, when you're really protecting that data plate, we appreciate it. It's so good because this tells us so much information about what the motor's doing and how we need to repair it, how we need to run it, how we need to do a lot of different things. So, when you look at all the different information that's contained on the nameplate, it's going to tell us the horsepower, the RPM. If there is a model number, it typically comes into play on a standard NEMA T-type T-frame motor. If there's a catalog model number, what the serial number is important for us if we have to go back to the OEM and try to collect some manufacturing data. We don't always get that from a repair side of things, but sometimes we do. But on a replacement motor, that's going to be beneficial because we can get you like for like. Like we can go back to the OEM, here's the serial number, they can pull it up, have all the performance characteristics, and they can build you an exact motor that'll drop in and perform just like your failed motor. Volt's really important. You need to apply the right voltage. Current is on there as well, and it's indicated in amps. What the frame size is, we'll talk about frame in a couple more slides coming up. But frame is really important as you apply the motor, because we want to get those dimensions correct, right? Unless there's a change, but if you have something that fails or if we're replacing a motor, we want to make sure we get the frame right so that you don't have to do a lot of base work, coupling work, alignment, a lot of different things if we don't get the frame right. We'll talk about type, phase, obviously it's going to be AC, so to be single phase, three phase, what your frequency is, and that's in this HC, which would be hertz. And then there's NEMA designs, that would be the we'll talk a little bit more about that, but that's the torque design. So we get into A, B, C, D type of a design. The insulation class rating, if you have a power factor requirement, we'll talk about a little bit more about power factor, and then service factor is here. We'll talk about service factor, but then sometimes they will list the bearing numbers on there, which is a big benefit to the repair shop, because if we know what that is, then we can get a little bit more accurate on our quote for repair. We'll know what type of a bearing that's in that, meaning that if you have a belt-driven side load and it's running a ball bearing in the front, probably not the best application, probably would want a roller bearing at that point. So bearings for that really help us. And then your efficiency ratings would be down here. Not everybody lists that, but some people do. If it's a precision balance motor, like an IEEE 841 spec motor, then that's going to be balanced to a certain standard. That's inches per second. So that could be listed on your nameplate. And then what type of grease. Grease is really, really important because you do not want to cross-contaminate or use different types of greases. If it's got a polyurea grease in it from the OEM and you go back to re-greasing the motor, you really need to use polyurea. We see a lot of failures that are caused from cross-contamination of uncompatible or incompatible greases. We see failures on over-greasing just as much as we see under-greasing and all that. So really nice when they put the greasing on the nameplate. But as you guys apply your motors in the field, what I would suggest, if you do have a way, if you're using like an asset tracking, some kind of management for your motors or whatever you're doing in the field, and you have the ability to take a picture of the nameplate and load it into the computer when it's legible and good, I would highly suggest that you do that. It will save us a ton of work later on if we have to come back and if the nameplate's either gone, knocked off, if we can't read it. These things go out in the field and they go in some really, really harsh environments. So the nameplate tends to get a beating, but that really is very important to keep that information intact as much as you can. It really helps the motor shop to understand what we need to do to either fix it or replace it, right? Okay, talk about horsepower. Horsepower is a rating that's really used, I guess, in the U.S. and in, I guess, in England, probably. Some other parts of the world, that's going to be, your horsepower is going to be rated in kW, but over here in the States, we use it as horsepower, and this is just kind of the history of that, how we got to that. But it was defined back in the 18th century by James Watt, right? So there you go, watt, kilowatt. He sold steam engines and asked how many horses, he was asked how many horses one steam engine would replace. So he had horses, you know, kind of through this graphic that walked around a wheel that had a weight in the bottom of it, and it lifted the weight, and he found out that the average was about 550 foot-pounds is what one horse could typically lift. So there you go. So our current rating of 1 horsepower is equal to 550 foot-pounds per second, or 33,000 foot-pounds per minute. So that is the history of a horsepower and how we got to it. Still use that today. And I mean, it's the rating that kind of everybody knows over in the States. And when we talk about speed and synchronous speed and poles, and you'll hear, you know, depends on how long you've kind of been around in the business or whatever, you know, you do, what your preference is. But there's some people that will talk about RPM in actual RPM, could be, as the table is showing, 3,600, 1,800, 1,200, or you know, they talk about 2-pole, 4-pole, 6-pole motor. In a synchronous motor, where you get something that is much slower turning, you know, we can get up to 22, 28 poles, 30 poles. It just depends. And the calculation of how to get that is pretty easy. You know, so if you want to determine how many poles your motor has, it's 120 times 60 divided by the RPM of the motor. So in the example below here, you'll see 720, which is 120 times 60 is 7,200, divided by 327 RPM gives us a 22-pole motor, right? And that's how you get there. Yeah, and then the example up here is for 2 poles. So yeah, if you have a 3,600 RPM motor, it's a 2-pole motor, right? So 120 times 60 divided by 2, 3,600 RPM. So you can do it the inverse as well, right? Okay, and then volts. We'll talk a little bit about voltage, and it was named in honor of the Italian physicist Alessandro Volta, and he invented, which was, I guess, arguably and quite possibly, which was the first chemical battery, right? So he's the guy that really kind of proliferated that technology. There's a little history on how the volt got its name, but you know, when we talk about voltages, you know, for us, there should be 3. This has got an error on the slide, but you know, we talk about low voltage, which is typically 208, 230, 460, 475 volts, 690 volts, any of those things. And then medium voltage is 2,300, 4,000, 4,160, 6,600. And then, in my opinion, once you get past 6,600 volts, it's usually high voltage, right? There's higher voltages above that, but when we talk about 7,200 volts to 13.8, you know, and for me, it's because that's the break in the insulation. You know, when we repair things and work on things, you know, the medium voltage resins and materials are usually rated at 6,600 volts and below. If we go above that, we have to change a lot of things, right? We have to change resins, we have to change materials, we have to change lead wire. You know, there's just a whole nother level to deal with past 6,600 volts. So I apologize, that actually should be down here. But you know, you may have especially on a NEMA T type of a motor, you may have multiple voltage, and it just really depends on how it's wound and the type of connection internally that it has. It could bring out multiple leads. Usually, if you have 3 leads coming out of the terminal box, it is 1 rated voltage. If you have 6 or 9 or 12 leads coming out, you may have dual voltage motors, which have the ability to run on multiple voltages, like we've seen. Currently, manufacturers are operating or manufacturing motors with 208, 230, 460 set, right? So that segment right there is the most common type of a 9-lead motor, and there's a connection diagram that tells you how to connect it. You got to get that right. If you don't get that right, you will fail the motor. It's because it won't feed through the winding correctly, right? Different voltages require a different connection. Okay. And then amps and current, there's a story to that as well. The amper is it was named after a guy, Andre Marie Ampere. I think that's how you say that. But he was one of the main discoverers of electromagnetism, as a matter of fact. And he figured out that there was a measurement of the amount of electrical charge passing a point per unit in time, right? So amps and volts are all relational, so it's, you got to get that one right as well when either sizing the motor or applying a control, or what you're doing with your switch gear. All that stuff is rated on voltage and current. So on the nameplate, we'll typically see what the full load amps are, and that is based on whatever the rated voltage is, because the voltage is going to have an effect on the current draw or the amperage. Inrush current is one of the things that we do have to solve for whenever applying a motor to a rated load. If the motor is started frequently, that's one of the things we'll try to understand on what's going on. But it can be as much as 650% of the standard line rated full load amps, right? There is a lot of electrical saturation that happens really in the rotor, because the rotor's experiencing so much slip. It's just trying to, a motor when it starts, it's just trying to get going as quickly and as fast as it can. So it just sucks in as much electricity and current as it can because it wants to start and go. So that's where we see a really big spike on inrush current. But those are things that we can also solve for, right? We can design and build motors that have a lower inrush current by design. Just depends on how we build the rotor. And then we can also apply either VFD or soft start technology that will ramp or soft start the motor so that we don't have as much inrush, which does save the life of the motor quite a bit. Right. Okay. So we talk about frame sizes. There has been over years and years and years. I've been doing this for a long time, so definitely not back in the 50s, but I have worked on pre-NEMA motors and U-frame motors, and over my 30 years in this business, all that stuff's just really, kind of changed. When you look at the difference between what the re-rate is, that would just be, after 1964, they standardized on a NEMA frame, T-frame motor. So all of the manufacturers, because pre-NEMA, it was very difficult to apply different motors to different things, right? Because everybody was dimensionally different. So NEMA got together and said, well, we're going to standardize on a frame size. It just makes things much simpler. So they did. That's went through a few variations, and you can read that up here. The U-frame motors were about 52 to 64, and they were predominantly applied in automotive manufacturing, but a much larger, more robust type of a motor, I guess that's the way to say it. But really, it was much larger because they just didn't have the advancement insulating materials that we have today. Some of the motors back in U-frame or pre-NEMA would use cotton on the wire. Now we have enamels, and we have other coatings that really allow for a much smaller package. But that was really part of the reason why those motors were so big, just because they had to have the large motor for airflow into it and for the ability to wick heat away. those types of things, just overbuilt, very much overbuilt. So you can see the difference in designs. So when it was a 1952 NEMA or U-frame motor, the dimensionally, the newer motors are much, much smaller, right? Much same horsepower, same torque in a smaller package, right? This all standardizes pretty much through this 445 TS frame. And really that is through any OEM. If they're manufacturing NEMA type motors, then the frame size is going to be consistent. Okay? And when I mean consistency, this is what we're looking at, right? So this is your frame dimensions. And as indicated, all the frames are typical through 445T, but where it needs to be consistent, and especially for the end user, would be on shaft diameter, shaft height. So dimensionally we're looking at, and if we were to replace a motor, we would want to make sure that we had these dimensions all accurate and lined up. So the U dimension, which would be the diameter of the shaft, and you can see it right there. The V dimension would be the usable length of the shaft. There's from the shaft height, which is the D dimension. So if you're looking, that would be from the base plate to the center line of the shaft. And the 2F dimension is I guess you would call that the length. So from the bolt hole back to the bolt hole front, what is that length? And then the 2E would be the width. And then BA would be from the front of the bolt hole to the back of the shaft. What's that length? Right. So when you think about applying a replacement motor or even a spare motor, you might have spares. That's where we have to get those things right, because your base plate's going to be set up and your bolt holes are going to be set up typically for whatever motor you have pulled out of there, right? And even your couplings and all those dimensions are pretty important, right? So that's why we ask those, and it's gotten with in the 60s and all that, it's so much better that we can all now say, give me these dimensions, and there you go. So we all know what we're talking about. Just a kind of an interesting thing here, if you really wanted to know what your D dimension was, which is the shaft height, there's some math, and it's all done through the same OEM manufacturers. But if you were to take the first 2 digits of the frame size and divide it by 4, that's going to give you your D dimension. So if we had a 6811 frame and we divided that by 4, we would know that we have from the base plate to the center line of the shaft, we would have 17 inches of shaft height, right? So it's just kind of an interesting thing. And then also when you get into the suffix, meaning the letters that come after the T, those mean different things. There's C, which is a flange. There's D, which is another type of a flange. There can be S, which may indicate short shaft. Then there's also a suffix of Z. And if there's a Z at the end, like if you have a 440 TSZ, there's something with that motor that's not standard. And it won't necessarily tell us exactly what that is, but that really does, and you can see some of the examples down here, but it indicates a special motor. So when we hear a TSZ or a TZ or something like that, we're going to ask more questions. Was the shaft longer or shorter? Is it threaded? Is it tapered? Does it have a step down in it? Whatever the case may be, that's when you get a Z at the end of that, just understand that that is a non-standard type of a motor. Right? Once we get above NEMA, because we talked about the standardization of NEMA, through 447T, there is above NEMA motors, and there's some consistency through it when you talk about 5,000 and 6,000 series frame sizes. But I'll be honest with you, that stuff really varies by manufacturer. So if we were to replace a large motor, that's where we would probably ask for a dimensional data sheet, and just to make sure that we had all of these dimensions the same, right? So and they don't even call it out as 2B, and the same type of nomenclature in the data sheet. So we would want to know kind of what the 2E is, what the 2F is, shaft height, all that stuff. You just have to verify that in above NEMA application. So anything that's going to go into 500, maybe 600 horsepower, medium voltage, anything 5,000, 6,000 frame, anything that may have a TWAC or a WP2 or WP1 type of enclosure that's square built, square bodied motor, those are going to be non-standard. We're going to ask for a little bit more information on those. Oops, went too fast. There's definitely different ways to mount the motors. The most common would be this F1 configuration, which that little box right there is the terminal box. So facing the terminal box or looking at the terminal box, which way does the shaft come out? Does it come out left or right? If it comes out to the right, that'd be what we call standard or F1 motor. If it comes out to the left, that's opposite standard or F2 type of a motor. Those are the two most common types. But as we get into different configurations on how you can mount motors, there's all kinds of wall mounts you can see there, and even ceiling mount. Ceiling mount could be considered, if you were bolting a motor to the undercarriage of a conveyor belt or something, basically where you're going to have feet up, that's going to be a ceiling mount type of a motor, right? And really it's not, there's some things that vary with it, really from, and it depends on the design of the motor. Sometimes we can't switch them. Most of the time we can. Let's just say that you bought a standard motor and it was an F1 type of a motor, which that's how they're usually going to come in an F1 design. But you need the terminal box and the shaft to come out on the left side. We can just do a shop modification and turn the motor around, usually. About 90% of the time we can do that. Not every time. It depends on where the fan's located at on the rotor. Some other things kind of go in there that may prohibit us from doing that. But usually on these ceiling mounts, you just take your motor, flip it upside down, and you can mount it to the ceiling. Usually the way it goes. On some of the wall mount stuff, we may ask you what you're driving. If it's a belt-driven load, we just want to make sure that the bearing would be appropriate for the driven load, right? Because there's different weights that are now being applied, from just from having the gravity and the weight of the rotor on a ceiling type of or on a wall mount configuration. So we may ask a little bit more questions. And then when we look at flanges, and a lot of flange motors out there, typical application would be a gearbox pump, any kind of eddy current drive, a clutch, a brake, something that the motor has to flange mount to. Those would be C-face, and the frame is going to indicate what that is. Like we can have a 215 TC. C-face would be that, right? So the usually, and it's the holes are drilled into the motor face, and it may be footless, may have a foot plate on it. It may or may not. It just depends on how you're going to mount it and what you need. But that would be, when you look at the motor on the lower left-hand side, that'd be an example of a footless round body C-face motor. All right. The motor next to it would be an example of a based C-face motor. And then we get into, if it was like let's say that you had a 256 TD motor. Well, the D is going to indicate D-Flange. The D-Flange is larger, and the bolt holes are going to be on the outside of the flange, and they're usually through bolt holes. So you would bolt through that into something, maybe a gearbox, maybe a vertical pump. I don't know, but that's the difference between the flanges, right? So it is a C-face and a D-Flange. That is the proper way to say that. And then we'll talk about vertical motors, and I think most plants have vertical motors in them. The most common application for that is a pump, water pump. It could be circulating pump, it could be booster pump, whatever the case is, but that is the typical application for vertical motors. And there's a couple different designs. There's a solid shaft and a hollow shaft. Hollow shaft, if you look at a multi-stage submersible pump, the shaft is going to come up and through. which is what this graphic in the center is indicating. So it'll come up and through the motor shaft, and then there's a locking nut that goes on top of that where we lock the motor shaft to the pump rotating shaft. And then a couple of things you have to do if you're familiar with how to apply these. You set the you will set the thrust on it. So as the motor turns on, it's going to have some lift to it as the pump is doing its stuff. So we can factor that in to how you apply the motor. Solid shaft is kind of the same, just a different method. Where the motor does have a solid shaft, it goes into a keyed flange into the sorry, I just got a message up there, but it'll go into a coupling, whatever the case may be, into the pump, and that's how it works. So solid shaft, vertical shaft, usually the same type of design of the motor. The windings and the configuration, terminal box doesn't really vary that much. It's just on how the pump shaft comes up and through, right? It's just a way to couple the motor. Okay, and the different types of enclosures, there's a few. So open drip proof, very common. That's one that if it was an inside application or even outside, but if you really wouldn't put that around a location that has a lot of ambient issues, meaning if it was a highly corrosive environment, if it's high dust, if it was out in the middle of a field somewhere where you had a lot of rodents and snakes and all that, I mean, they will find their way into a motor. So open drip proof runs really cool though. I mean, it's the best way to really do it, but not the best application for ambient conditions that are unstable, I guess I should say. Totally enclosed, non-ventilated. This would be an application if you had an air over motor. So if you were putting this on a belt driven fan where it's going to draft air over it, then that would be a good application for TENV. TEFC, which is really common, would be, has a totally enclosed design with an external cooling fan included in or inside of a shroud. And as it rotates at whatever speed it's running at, then it's going to blow air over these cooling vents, and that's how it cools itself. So really common application, really good for outside, really good for high dust environments, something like that. Just keeps a lot of stuff out of the motor. Then a totally enclosed blower cooled motor would be a good application for that. Is if you're running a VFD that the motor could potentially run slower and doesn't have the ability to cool itself, then we'll add an external blower, right? So the external blower just runs at a constant speed, so it keeps the motor cool. So if you have a VFD application and you keep losing motors because they are running hot, then we may want to add a blower to it. When you get into medium voltage motors and higher, then the enclosures start to get a little different. You have a NEMA weather protected type 1 or WP1. There's WP2, and I know this is just hard to see because it's a little small, but it just shows you the air-to-air exchange and how that works, right? So there's fans basically on the rotor that blow air out and they draft it from the bottom, and it just exchanges air to air. WP2, similar design, but a little bit more weather protected for rain. There is a totally enclosed fan cooled design, which is there. There's an air-to-air cooled or a TAC motor, and you can see heat exchangers in there. That's what that tube bundle is. And there's also a water-cooled application, and if you're using chilled water supplies, you probably have these in your plant, which is a tube bundle that has more than likely some kind of glycol solution running through it, and the motor will have fans that then blow up and through and down, so it's like a circulating coolant. Doesn't really get into the motor, it's just in the top hat design where the tube bundle is, but that's kind of how it cools itself, and that was called a totally enclosed water to air cooled motor, TWAC. See a lot of those on high voltage motors, high voltage induction. We'll see a lot of TWAC. operations. Right. And we're running out of time here, but talk about frequency just real quick. Frequency is represented in hertz, and a guy named Heinrich Hertz came up with that. And it really is just the number of cycles per second. So electrically, how many cycles per second is your rotating field going? So typically in the U.S., it's 60 hertz. That's what we run off of. We do see some 50 hertz. It just depends on what your plant does. But that we need to understand that if we're either testing your motor, repairing your motor, or whatever. Again, that's why it's important to have them on the nameplate. But you'll see here that this example showing that an 1800 RPM motor operating at 60 hertz, if you had 50 hertz, it would run slower, right? So it does have an effect. Yep. Yeah, and that's a good point there too. If we get into metric motors, if we get something from overseas, that is one of the things that we're really going to verify. Is do we got a 50 hertz motor or a 60 hertz motor? And that's the things that your motor shop should be asking, or are you asking them or asking you, just to verify that frequency if you are indeed using a metric frame motor, because it's going to make a difference. All right, torque. And we talked earlier, this would be, when you talk about the design of the motor and on the nameplate, if you recall, there was a design, and that's what this is really indicating, A, B, C, D. And then this would be the different designs of the rotor bar, right? And for those different designs, we're going to get different torque requirements, right? So if we need high slip, as in like a hoist, a winch, elevator, extractors, anything like that, then we would use that design D type of a motor, right? Design B is pretty standard. And usually, I'm probably 80% of all the motors out there usually design B, which would be that construction of a rotor bar. But it's about 1.5 to 3% slip, normal starting torque, there. But if we did need anything else, then we can do that with the design of the rotor. Right? A variable speed drive can eliminate the need to have these, because the VFD will then you're able to program in whatever requirements you need the motor to do from a starting perspective, right? So you can just go with the standard design B type of motor as long as it's VFD rated, and we can make it work. It's just the difference in the way the torque curves look from A, B, C, D design, and it just kind of shows the relationship of speed versus torque. And then in insulation ratings, this is important because I don't know, like we get into this conversation a lot, especially on specs, when folks are asking us either, especially when we're winding something, what we use are Class H materials in our rewinds, but most of the OEMs are using Class F materials. Okay, and that's the difference. It really is the difference on what the winding temperature has the ability to operate at. So maximum winding temperature, that's what that is saying, right? So if you start with a maximum ambient, and this is how the rating goes. So maximum ambient of 40 degrees C or 104 degrees F on a Class H design motor. In order for it to be a Class H motor, every component in the motor, from the electrical aspect, not really mechanical, but the lead wire, the insulating materials, whether that be your slot liners, your wedges, your sticks, your phase paper, anything you're using in there needs to be rated Class H. If it's not, then it's not a true Class H. And we have seen that a lot, where some people cheat that. They'll use Class H materials in the winding and construction of the motor, but use a Class F lead wire, and it's not a Class H motor at that point. It's Class F. So, but at any rate, like Class H should design maximum, and this isn't maximum over ambient. This is maximum operating temperature at 356 degrees F. Right, so you can see that the difference between F and H, especially down in Houston. If you're running full load, the motor is going to have it's going to produce its own heat, and it's going to be shedding the heat, right? So then you add whatever the ambient temperature to that is, and then Southeast Texas, where we're at, I mean, it gets 100 degrees down here quite often. So, you can definitely see where another, 55 degrees really helps, or 45 degrees helps. So that's really why we use the Class H materials, right? It gives us a little bit more ability to operate in a very harsh and hot environment, right? And well, that's important. Hopefully this next one's up here, but yeah, if you're running into a service factor, that insulation class rating is going to be critically important. Honestly, what the service factor really means is it's the motor's, and I'll just read it. It's the motor's capacity to deliver continuous horsepower beyond its nameplate ratings under rated conditions, right? So if you have a motor that is a 100 horsepower motor, it's drawing 100 amps, just for the sake of math, we'll use that, but it has a 1.15 service factor, you can run that motor past the 100 amps and into, you can do the math there, but you can overcurrent the motor for a little while. So it just gives you a little bit more room. Where that would be important is if you had a pump that may not have a consistent load, like if it had varying viscosity in whatever it's pumping. Crude oil is one of those things. It could be, a certain load here, but you get a big slug of something in there, then the motor has to ramp up, and it has a little higher current draw for a minute, a higher service factor of 1.25, and they even go up to 1.15, 1.5. That will be able to soak that up. If you have a production demand where the motor runs X amount of feet per minute on whatever conveyor or whatever it's doing, but you need to ramp that up a little bit because you're maybe behind on production or you want to get a little bit more, you'll typically see motors run into their service factor. They do produce more heat, which is why that insulation rating is really important. If you're operating a motor into the service factor on a very hot day and you don't have a good insulation system, the motor's going to fail at some point, right? It just will. So that's kind of the relationship between service factor and insulation rating. Okay, talk about bearings. There's a few different kinds of bearings: anti-friction bearings, sleeve bearings. Sleeve bearings can be in multiple configurations, just as much as anti-friction bearings could be. There's angular contact, there's roller, there's ball, there's max ball, there's different edges, I guess you would say, or construction of the bearing journals. You can have a J design, you can have a U design. There's multiple things. There's just a ton of different types of bearings. But on the NEMA, most standard type of a motor that we see, it's going to be a regular anti-friction ball bearing, right? You get into larger motors, it's going to be usually a sleeve type of bearing, and this is a picture of one on the top right, where that's a sleeve or a Babbitt journal bearing. There's a whole bunch of different things that people call it, but be a few different components in there. You're going to have the top shell, the lower shell. You're usually going to have two seals in there. That big brass ring there would be a slinger, which goes into a reservoir, picks up oil, and slings it over the shaft. That's how it gets its lubrication. How these typically work is they ride on a film of oil, right? So it's a really thin hydrodynamic effect. So it's a hydraulic lift. So really, the Babbitt holds the oil as it rotates, it flings up around, and then you get separation between the Babbitt and the journal bearing. So really smooth, low vibration type of applications. Really good, very long life type of a bearing. Different methods on how to lubricate that. You can have forced lube, you can have oil bath, you can have pure oil mist, a bunch of different ways to do it. All right. So pretty much in larger motors, we see shaft journal bearings, and if if you're dealing with your motor shop, make sure they know how to work on those, because that is not your normal animal, right? There's different wear that you have to get in there. There's definitely tolerances you're going to have to hit. So they need to have some experience on how to repair journal bearings or sleeve bearings. Okay. And then just on motor efficiency, there's a bunch of different designs on efficiencies. We've seen a lot of movement in this from the new motor perspective, where motors used to be about, gosh, back when it was a standard efficiency motor 20 years ago, could have been 80%, 85% efficient. Now they don't even manufacture those motors anymore. The new requirement is everything is premium efficiency. So, really, and that really has a lot to do with how much electricity is used by electric motors and just in the grid in general, right? There's just a ton. How efficiency, it's one of the things you want to look at when you're applying a motor or buying a motor. This example right here is showing a 5,000 horsepower motor, or $5,000 motor would be typical cost for 100 horsepower. But that $5,000 motor could use as much as $35,000 a year in energy. And we can help you understand if there is some opportunity to apply a VFD on a reduced load, to really drill into what that motor's running. If it's fully loaded, it is what it is, right? But if you have partial load, and we have an opportunity to kind of turn the motor down from a frequency perspective or a speed perspective or a load perspective and draw less current, then there's definitely a payback scenario there. And that's really why we put this slide in here, is to understand that efficiency is relational to the application, right? If you have something that's just needs 100% load 100% of the time, then, well, it costs what it costs. But if it's a varying load, then we may be able to help you out and save you some money. Just real quick on rotation. Rotation is, and the reason that this is in here is, like, if you have rotational fans that are directional, we'll make sure you get that right. We've seen motors come in that have failed because somebody has hooked it up backwards, and the motor ran backwards, got hot, didn't cool, and it failed. So, we can help you understand if you have directional rotational fans on your rotor. If you don't, if it's a unidirectional motor, fine, no problem. But there's, depending on how the motor is manufactured, that may be the case. So you want to just understand if you do have rotational limits, and we can help you with that. And then on hazardous areas, there is a UL certification and the UL design of a motor, Underwriters Laboratory, and that's really what these are talking about. So when we talk about Class 1, Div 2, group whatever, that's what we're talking about, right? And you may have applications in your plant where you're using hazardous certified or explosion-proof motors, UL certified motors. So if it's a Class 2, Div 2, right? So it would be Class 2 combustible dust, Division 2 not present in normal operation, but could be present in abnormal operation. And then even down into the group of this is what it is. So if you were at a grain silo, right, you would probably be using Class 3, Div 1, Group G, right? And what that is it really is if the motor fails, if there's an electrical failure, in motors, typically when they fail, there could be an electrical arc that gets out of the motor. And if you guys have been around motors long enough, everybody's seen it. The smoke gets out, right? So with smoke, it could potentially be a flash, and you do not want your electric motors flashing if they fail. So the motor is designed to contain the flash if it fails. And it's also designed not to ingest some of these materials. I mean, when you look at the construction of a hazardous or a UL approved motor, really long flange areas, even on the terminal box, it's all very long flame path areas to kind of extinguish that. So the design of the motors is completely different. They do cost more money new. They do cost more money to repair. And the reason that they cost more money to repair is that we have to go through all of the different dimensional designs of the motor. So we have to measure the flame paths, look for anything that could potentially allow an arc to escape. And then we have to have the motor recertified. So we do have an inspector that actually comes in. We present, this is what's going on with the motor, and if they approve it or don't approve it, and issue a new nameplate. So there's a cost associated with it. But not every shop can do UL recertifications. We can. So if you need that, certainly here to help you. And this would be, just a little bit more about hazardous location motors and kind of what the temperature design is. They really are required to meet a certain temperature design too, right? So if you have UL applications and you need help understanding what those are, or even if you need a UL motor in there and you maybe want to derate or declassify that UL area, because I'm sure there's insurance exposure to those as well. We can help you with that too. We can help you understand if you really need to have a UL motor in there or not, right? May not be necessary, might be. If you have noise requirements, there are dB ratings on motors that we can go in and help you understand what that is. We can do sound abatement. Most of the manufacturers, if we give them a requirement, they'll tell you if they can do it or not. You may have a requirement for dB. That would be, if we had maybe a fan isn't the right application. Maybe you can't have an external cooling fan. Maybe we have to go with the TWAC design, something like that. So if you have a sound requirement, motors are designed to run at a specific sound, right? So when you look down here at the best effort, and it's typically the IEEE standard is 85 dBA. And that's usually where it's going to be. But if we need to get better than that, then we can help you. All right. So got to this one and try to get through this fairly quick, but this is where I really wanted to spend some time just talking about why motors break and what we see as the most common type of failures. And this graphic really does show very good on that a majority of the failures that we see come into the shop are mechanical in nature. They either be a rotor failure, a bearing failure, something contaminated the motor ingested something. We just see a lot of that. Very close second to that is an overloaded condition. Overloaded conditions can affect the winding. If you overload the motor, run it past the service factor, or run it in a high heat ambient condition that the motor's not rated for because it doesn't have the insulation rating, you'll start to see the insulation decay and degrade over time, and then that's where you'll see failure. Overloading a motor, running it past its rated load requirement, so if it's rated for 50 amps and you run it 60 amps, you're overloading the motor. And so the motor's producing more heat that it's not designed to wick away or cool, right? It just can't cool itself. So that's where we see an overloaded condition. How that happens, the insulating materials become embrittled, right? It loses all its flexibility, and eventually it just cracks, and a crack in the insulation is a very good pathway to ground. And that's typically how they fail. We'll see either phase-to-phase failure, turn-to-turn failure, or we'll see something fail on the slot. That's usually where those happen in the windings when we see an overload. And it's just like a very dark baked type of, you can tell the windings have been hot when it's overloaded. Single phasing happens. If you get a power outage, lightning strike, motor will single phase, and then just old age. Over time, motors just die. They do. The materials for winding and insulating have gotten a whole lot better over time, and I think that the longevity has followed that. When we went from when Nomex came around, and which is the materials that we use on our rewinds, you start to look at a laminated material like a Dacron, Mylar or Dacron. Those materials cheaper will delaminate over time, and then it'll fail. So Nomex gives you the ability to stretch the life of the motor out, right? So, but over time they just get old and they just get embrittled, just like I said. But it could be if motors applied correctly, maintained correctly, you could have a winding that lasts 40 years easily. But you will have to maintain it mechanically, because you just won't get 40 years out of your bearings for sure. So some of the things we see that come in, not everybody gets it right. Even the manufacturers have the ability to get it wrong. So we do see defects in material or labor. Misalignment's a big one. Misalignment will cause excessive vibration, cause heating issues that could affect the winding. Incorrect bearings. So if you have a ball bearing on a cooling tower that's a axially driven or a side load, that's going to be a misapplication. One of the things that we see a lot is people using 841 type of motors, IEEE 841 type of motors, when a API 661 spec motor is the right one to use. The API spec motor is designed for cooling towers, belt driven loads, right? So that's kind of where those are at. We can help you understand what that is too, if you have your motor applied correctly. Insufficient or over lubrication of bearings, that goes both ways, right? So if you don't grease your bearing, it's going to fail. If you over grease your bearing, it's going to preload, and because you're putting pressure, grease pressure, so now the bearing has to turn against a lot of grease into its rotating design. So it's got to handle the load, plus it's got to run through a bunch of grease. So what happens on an over greased bearing is that it just creates more of a load, and the bearing will heat up, and as it heats, it expands past what its normal design would be, and then you start to see failures just from a preloaded, over greased motor. Rotor damage, we see that. If you start your motor and there's a chart to every motor, how many times it can be started per hour, if you exceed that, you will more than likely cause rotor damage. And we do see that. That's indicated in failed end rings, broken rotor bars. A lot of different things happen when you start your motor. We talked about overload and operating above the rated limits. Single phasing can be lightning strike, or just if you have power conditions on your bus. Harmonics from VFD, definitely seen them. We've even recently, if you're running a VFD and you're not, depending on the VFD that you have, the configuration, how long the run of cabling is, a lot of factors go into if the harmonics of the VFD are going to cause issues either in your winding, or they can cause fluting in the bearings, right? So you will carry shaft currents into the bearings, and they'll fail mechanically just from harmonics and electrical current running through the shaft, right? So there's ways that we can get around that, though. We can help you with that. If you have a VFD and you're experiencing unplanned failures and don't have a lot of reliability in that, we can help you. Corona on insulation on 6600 volts above, it's always there. We do a lot of design in high voltage motors to keep corona at a minimum, but it is present, and that's when we will, if you send us your high voltage motor, we'll work with you and understand what your application is and design a coil that mitigates corona as much as possible. But it is in a high voltage application that is more than likely over time, it'll just kill the motor over time. What it is voltage that is on top of the coil, so you can contain some of it, but you're going to get some escape just because of the nature of high voltage energy inside of a conductor. It will escape, and eventually it just eats and etches through the insulation and will work its way to ground, and you have a failure. So insulating materials and some other stuff that's all coming online for high voltage stuff is very encouraging as far as the mitigation on corona. So if you have some high voltage stuff and you want to have a discussion on what the newest technology is on insulation and corona mitigation, we can help you. And then in incorrect voltage or incorrect rotation on larger 2-pole motors, talk about that, and then water entry into just water ingress into a motor in general. We do see that as well. Obviously water and electricity don't mix very well. So it really depends on what your enclosure is and how you have that applied to your load. When we talked about the ODP, the open drip proof motor, that may be prone to water entry if you have it misapplied. Right? Just some stuff on factory testing. If you buy a new motor, you can request standard or complete engineering tests. That's all available to you. We can help you understand what those options are. We can also do all of these services at all of our service centers. So in Houston and in Houma, we can do all this factory testing for you as well. So yeah, just understand that's all available. If you want to have a motor proven out before it's installed, anything that we repair is going to go through the test panel. So it's going to be run, and we're going to check vibration, we're going to check temperatures, we're going to check current. There's a lot of different data points that we collect on a test motor so that we make sure that we're delivering you a good product. If there's more requirements to that, normally we can accommodate you. I haven't seen a whole lot we can't do on a test panel. And in some cases, we do have the ability to do more than what an OEM can do. So just keep that in mind. If you have some special things that you want to get tested, if you bought a motor that's new and you want to get it proven out, we can put it on the test pad and we can do that for you. Just let us know. And then really the last slide here is on warranty. And I think that warranty is really there for your peace of mind, right? Do we get it right all the time? No, absolutely not. I mean, things happen, with either insulating materials, they may have installed something wrong, so things absolutely happen. But just want to talk about what a standard warranty is typically from either a repair service center or an OEM, right? And I think that most of your better shops, repair shops, are going to offer at least a 1-year warranty on their rewind. I mean, at least. There are others that offer more than that. We are the company that can offer more than that. It just depends on the application and how we're partnering on that motor. But there's some that may not even offer 1, 3, 5 years. And if you're doing business with those guys, you may want to question why they aren't confident enough in their product to go at least 5 years on a motor, right? So a standard motor from an OEM, is going to be a 1-year warranty, energy savings, 3 years severe duty, 3 years. IEEE 841 motors, all now, I think most all of the OEMs have aligned where that's a 5-year warranty on that IEEE 841 motor. And the reason that is they really spend a little bit more time getting the vibration right. It's an oversized bearing. They have bearing isolators and seals on each end of it, so it really doesn't have a lot of ingress of dirt and contamination inside the motor. It's just a much better built motor, right? So that's why you see the longer warranty. And then a large motor, you can go 1 to 5 years with conditions, and typically the conditions on those are on a large motor is that we would want to have Dustin and his field service group come out every so often and just check the motor and make sure everything's operating correctly. Want to collect some vibration data, maybe look at a PDMA so we can get some electrical analysis included in the motor, and just make sure that the wellness of the motor is intact, right? And that's how we would partner with you. So I think on your better service providers, they will have options for you on warranty. And I just don't like when somebody just puts a warranty on there and says, okay, you're on your own, right? If they're not willing to come out and say, look, we're just going to send a tech out and take a look and just make sure everything's good. It's not to make sure that, not for us to get out of a warranty or anything like that's not what it is, but it is really as a partnership to make sure that you're getting as much reliability out of the product that we created for you as possible, right? So that's why we partner with you. And I think that's it. And we went a little bit long. There was a lot more in there than what I thought. So apologize for going a little bit long. Hopefully you guys hung out with me for the whole time. Hopefully there was good information in that. If you need anything else or any other questions or any comments, the numbers are right there. You can call 713-748-0702, and that gets you to the Houston Service Center and gets you talking to me. If you need Dustin for field service, he's available, or Dan for engineering. We can get you in contact with those folks too. But again, folks, really appreciate you taking the time and let me ramble on about something I love, which is fixing electric motors. So I wish you all a great day, and I'll give it back to.
Thank you, Kevin. And
Thank you.
unfortunately, we don't have time for questions today, but we will do our best to reach out and answer all of your questions after the meeting. So on behalf of Ward Leonard and our presenters, thank you for joining us today and have a great rest of your day.